Greetings and welcome to another lecture in statistics. We're going to continue now with the correlational coefficient, basically giving you some additional information about the number itself. So in the last video, we talked about how to find the correlational coefficient. And so we found the value of R, either through using the z-scores or using the one step but more complicated computational. We would be able to find the value of R. Remember, R is anywhere between 0 and plus or minus 1. And the closer that R is to plus or minus 1, the stronger the correlation is. Now, it's possible as sort of a rule of thumb to interpret the strength of the correlation, depending basically on what R turns out to be. So it's good to know these. If it's at 0 to plus or minus 0.2, we're talking either no relationship or a very weak relationship. And in fact, this is not uncommon when we're talking, particularly in psychology, in that the relationship might be very, very weak, so that the two things might be related to each other, but very, very distantly. A 0.2 to 0.4 plus or minus for both is a weak association. 0.4 to 0.6 is a moderate association. Psychologists are very happy if they find this level, by the way. It may seem small, but it's not. 0.6 to 0.8 is strong, and 0.8 to 1 is very strong to perfect, and we almost never find those. Those are very rare. It is possible to find some correlations that are that high in psychology, but yeah, like I said, it tends to be very rare. Now, what in a way is even more interesting than R in telling us the strength of the correlation is what's called the coefficient of determination. And the coefficient of determination lets you know how much variation in one variable is attributable to variation in the other variable. So how much variation in X is attributable to variation in Y and vice versa. And the way to find that is, first of all, you find R. You take R, you square it, and that'll give you the percentage. And if you multiply it by 100 and, put a percentage mark after it, that'll give it. So if you have a moderate association, if you have 0.5, for instance, plus or minus, it doesn't matter because you're going to square it. 0.5 squared is 0.25. You multiply that by 100, we've got 25%. So 25% of the explained variance comes from that association. It, of course, means that 75% of the variance comes from something else, but it still gives you a good idea of how much, what is the importance, perhaps, of one of those variables on the other variable. And in fact, this is a lot of times what is really important. I mean, R is interesting. People talk about correlation. But what's really interesting and what gives us more information is this coefficient of determination. Is this R squared? So with that, how would we test a null when we're talking about this? How do we go about it? Well, the null is simple. The null says, if we're going along with the null hypothesis being there's no relationship, in this case, the null hypothesis is R equals 0. And then, of course, the alternate hypothesis is that R is something else. And as usual, we have a critical value. We need to find what the critical value is for a degree of R. And if our R is more extreme than that, then we know that it's significant. I mean, we've basically done this before many, many times. And it just so happens, just like before, we have a table. There is a table in the back of the book. There will be a table attached to the formulas, along with all the other tables that you might need. In this case, you basically look for, okay, what is our alpha? Is it 0.1, 0.05, 0.01? And then you do degree of freedom. And degree of freedom for a correlation, sorry about that, for correlation is n minus 2, where m is the number of pairs. N is the number of dots on that scatter plot. Okay, n is the number of points where you have both x and y. So you can think of it as pairs, as cases, any way you look at it. It's n minus 2. That gives us our degree of freedom when it comes to correlation. So we got correlation. Okay, that's great. As usual, as I said before, if it's more extreme, it's significant, we should reject the null and so forth. You know that. But I put it down anyway because it can't be repeated enough times. So what about this regression thing? What does regression do? What is regression? What regression allows us to do is to make predictions. And quite frankly, a lot of science is about the ability to make predictions. If we have this, then it means we're going to have that. And in this case, for instance, we can make predictions about a y value on the basis of a known or unknown x value. Okay? Now remember, if we were kind of talking about x being the independent variable and y being the dependent variable, we could then say, okay, if we manipulate this variable x, it's going to cause a change in y about this much. Now we can't know why, remember. We can't know what exactly is causing it, but we can predict. Correlations allow you to predict, even if they don't allow you to find cause and effect. So what do we need to be able to do this? Well, what we need to be able to do this, quite frankly, if you use the conceptual formula, the one with the z-scores, and not the computational formula to find your r, you already have them. You basically have everything that you need for this formula, which I'll talk about in a little bit. Because what do we need to do this? We need the means, and we need the standard deviation of the raw scores, which we have. Okay? Now, when we're talking about regression, you'll hear talk about what's called a regression line, or the line of best fit, or the least square line. Do you remember when I was pointing out in the prior video about how when we have a linear relationship, you could almost draw a line? This is the line. Okay, this is the line that you could draw to be the line of best fit, the line that best explains or describes the relationship. And it's very precise. Okay, this is not something where you just look at it and go, oh, I think it goes like this. This is something where with this regression, you can find this best fit line. Okay, and basically go through and say, okay, for each x, let's find y. Let's draw that line. Let's see how well it fits our data. Just out of interesting. So what do we do here? We minimize the distance from our cases to this line. Okay? We minimize it. So the squared of the distances from the distance between the points of the line is minimized. It's going to make more sense, I think, when it's not in words. Okay? And when we have this, we'll be able to predict a value of y given a particular x. We'll be able to predict, what that perfect line would be given a value of x. So what is the equation? The equation is y prime equals a plus bx. So, this looks a little bit, if you remember back from geometry, it looks a little bit like, finding the slope and that sort of thing. And it is related to the slope if you think about it, because what is the slope? The slope is, if you go this far on x, how far do you go on y and in what direction? And that's kind of what we're doing here. We're finding a line. We're finding the slope of the line. Now, y prime is the value we're trying to predict. Now remember, this isn't going to be perfect. This is an estimation. How good it is depends on how linear your equation is in the first place. A is where the regression line crosses the y-axis. Again, if you're having flashbacks to finding the slope of a line, that's intentional. B is the slope of the regression line. The amount of change, in other words, the amount of change in the y associated with the change in the x. Okay, so yeah, this makes sense. We're trying to find y prime. What do we need? We need where the regression line crosses the y-axis. We need to know the slope of the line, and we need to know where we're at in terms of x. So what do we need to find? We need to find a and b. Okay, we have x. We're going to find y. We need to find a and b, because a and b will be the same for any point on this line. The only thing that's going to change is x and y prime. The intercept is always going to be the same. The slope is always going to be the same. So once you find a and b, you should be able to draw a line to predict where the line should be given any value of x. Okay? So how do we find a and b? Let's start with b. Come on, computer. Sometimes it decides it doesn't want to give me what I need. Okay. B is equivalent to R, the Pearson's R, multiplied by the slope of y over the, or excuse me, not the slope, excuse me, multiplied by the standard deviation of y over the standard deviation of x. Okay, and remember, you already found all of these if you use the conceptual formula. You've got the standard deviation of y because you needed that for the z-score. You've got the standard deviation of x, ditto, and you found r. So as long as you have that, you can find B. And A is equivalent to the mean of y, which you've also already found because to find z, you have to subtract the mean from each score, minus B, which you just found, times the mean of your x, which you already found because you needed that to find the z-score. So you can see how the conceptual formula, it basically gives you everything you need. You take those numbers, you tweak them a little bit, and then you start plugging x's in, and when you plug the x in, it will then give you y. But wait, I hear you cry. This is an estimate. We can't know precisely where y is because it's an estimate, right? And yes, it is. And so therefore, what do we need to do? We need to find our old friend, the standard error. Remember the standard error way back from like January and early February? We need to find the standard error. What's the formula? There it is. The standard error is equivalent to each y-score minus y prime. So once you've found y prime, you need to go through and plug that in here. Y prime basically will give us, for x, y prime is where we're going to be on the y-axis for wherever we are on the x-axis. So we need to take y minus y prime, find the difference, square it for all the points, okay, for all of y, for each point of y, and so then it's divided by n minus 2. Okay? It's divided by n minus 2, which is kind of annoying, but there you are. Once we found it, you multiply it by the standard error units for alpha. For instance, a 0.05 alpha for a two-tailed test, since that's what we're talking about here, remember? It's two tails because it could be plus or minus. So this is 1.96 times our standard error. And that is, you need to add that to our predicted value to give us a range. So pretty much it's exactly what we've done before in terms of standard error. So if y is 1.67, great. Multiply the standard error by 1.96 and both add and subtract that value from 1.67 to find the range. There we are. Okay. So, and that will give us the range. It'll give us a confidence interval that'll have a correct estimate 95% of the time because we're multiplying it by our alpha. And there we are. That is the regression analysis to go along with our correlation to find a slope for our line. Remember, again, homework, all the questions from the textbook, email them to me before your test, and be as thorough as possible.